All right, we had talked about how you could convert between volume and mass and the number of apples by going through the unit dozen, the number of dozens of apples. Similarly, we can convert between volume and mass and the number of particles for having much smaller particles such as atoms, molecules, or formula units, all by going through the mole. The mole is like the dozen, except instead of being 12 of something, a mole is 6.02 times 10 to the 23 of something. And so we say that 1 mole of representative particles is equal to 6.02 times 10 to the 23 representative particles. What do we mean by representative particles? We can mean atoms or molecules or formula units. We know that we're dealing with a certain number of atoms if we're told that we have a certain number of moles of a non-diatomic element. So for example, if I said that we had 1 mole of carbon, we would say that we have 6.02 times 10 to the 23 carbon atoms. If we had a mole of, say, oxygen, gas, O2, well, that is a diatomic element. Together, those 2 oxygen atoms form a molecule. And so you would have that number of molecules. Another example of a type of molecule would be, say, CH4, having 2 nonmetals together. And then we also have formula units. So if you have an ionic compound, then you have a certain number of formula units within a mole of that ionic compound. So as an example, you have ammonium chloride, NH4Cl. Here, although everything is a nonmetal, we have a polyatomic ion and hence another ion as well. Another good example of a formula unit would be, say, calcium chloride, a metal and a nonmetal. You know this because you have an ionic compound, metal and nonmetal. Now this number, 6.02 times 10 to the 23, is a little bit strange. Where do we come up with it? Well, it just so happens that this is the number of atomic mass units within 1 gram. You may recall that AMU, or atomic mass units, they are about the mass of protons or neutrons. So there are about 6.02 times 10 to the 23 protons that would make up 1 gram, which you could scale out in the lab. And so because of that relationship, we can say that though 1 atom of carbon on average, considering all the isotopes of carbon and weighting their average on Earth, you find that 1 atom has a mass of 12.01 atomic mass units, and similarly then 1 mole of carbon has the same number, 12.01 grams. And so that 12.01 atomic mass units, that is called atomic mass, the mass of just an atom, whereas the mass of an entire mole of something is the molar mass. Similarly, we can find the molecular mass and the molar mass. Those will be the same number as well. Molecular mass is the sum of all of the atomic masses of the atoms within a molecule. So if you have CH4, you've got 1 carbon and 4 hydrogens. So the mass of an entire CH4 molecule is just the sum of all of these masses. And so you can calculate this by developing kind of a series of equations. You can consider the mass coming from all of the elements. So for example, carbon. There's 1 carbon, so we multiply that number of carbons, 1, by the atomic mass of carbon, 12.01. So that means that 12.01 atomic mass units is coming from carbon, and then we also have 4 hydrogens. Each one has a mass of 1.01 atomic mass units, so there's a total of 4.04 atomic mass units coming from all the hydrogens within this molecule. And so the molecular mass is just the sum of the masses of all the elements. It's 12.01 plus 4.04. It's 16.05 AMU. Now, a 16.05 atomic mass units is the molecular mass, but the molar mass is the exact same number, 16.05 grams. That's the mass of 1 mole of CH4, methane. But we also can calculate the formula mass and the molar mass for ionic compounds. So let's say that you have one formula unit of calcium phosphate. How many atomic mass units of mass does it have? Well, calcium phosphate is, let's see, CaPO4, right? Calcium and phosphate. Oh, hold on. You have not really thought about writing a compound which can exist. You haven't considered the charges of the ions yet. Calcium, you know, if it's an ion, has a 2+ charge, and phosphate, you know, has a 3- charge. And so calcium phosphate is not one of each thing. It's actually crisscross, can have 3 calciums and 2 phosphates. This is calcium phosphate. Please be careful when you're writing the molar masses of ionic compounds. Be aware of charges. And so the molar mass of calcium phosphate is multiply the number of atoms of each element by the atomic mass of each element, and you should find that the molar mass of calcium phosphate is 310.18 grams per mole. So the molar mass, so the mass of a mole of calcium phosphate is 310.18 grams. But also, the mass of a single formula unit of calcium phosphate is 310.18 atomic mass units. We call this the formula mass, the mass of a formula unit. And we also have the fact that 1 mole of gas occupies a volume of 22.4 liters. So this is kind of the size of a medium-sized beach ball. But this is only the case at one certain set of conditions. You know that if you take a balloon and you put it in the freezer, it gets smaller. The volume of the certain amount of gas in that balloon changes as temperature changes. Similarly, it would change if you were to let it go 1,000 feet up, where there's a different pressure. And so this equality depends upon you being at this certain condition, at STP, standard temperature and pressure. Now this is 0 degrees Celsius, and this is 1 atmosphere of pressure. By the way, 1 atmosphere of pressure is the same as 101.3 kilopascals. These are both units of pressure for gases. Thanks for watching, guys.